Can you hear me? I'll start sharing the screen if you can hear. Okay, fine. Um, so let's start this thing. Okay. Let me just drop a message if you can see the screen. Think I have started recording. Yeah, recording is on, and I'm sharing the screen. Um, you can see the screen, right? The the sketch pad. Okay, so today the problems are on topology, topology on real line. So I mean, as I typically do in our all the sessions, let's quickly go over the things that are required to solve the problems or understand, right? So these concepts are open sets, closed, and compact sets, and what else? Dense. I think this is fine. This much is fine. Perfect. And there is something called as connected, but I didn't think so. It's required to solve today's problems, connected sets. Okay. So yeah, to talk about all these things, first we need to know the things such as limit points, and interior points. Okay. So anyways, I mean, I'll quickly recap what is a limit point is. So let's say there is some set a subset of some ambient space called with some metric d, right? X is associated with a metric d. Now we call a point P as a limit point of set E. Limit point of set E if any neighborhood, okay, any neighborhood that you draw around P should intersect E phi should not be empty, basically, right? And this intersection, this set, whatever the non-empty set, cannot contain P. But basically, it should intersect E at any point other than P. Right? That's the definition of limit point. P need not belong to E in the first place. Okay, one simple example is consider this sequence 1 over n. N belongs to natural numbers. What, where does this sequence converge to? Call this a set A. Where does this sequence converge to? You can write, it's better if you try,
0.
right? It is 0. That's good.
0.
But does 0 belongs to this set A? Set A. Does this
No.
0 belong? It will never belong to this set, right? Because for that n tends to, it has to be infinity. But for any given natural number, this will not. So this is how it goes. If this is 1, and this sequence reduces rapidly, right? Contains points, many points here, and finally it is 0. So what I was saying is, you take any radius. I mean, in R1, the ball is open set. Okay. Now take any radius around 0, it will intersect this set, right? For some n, you can find some number belonging to this set. Any radius, any small radius you can take. Any small radius, you should be able to find some number between 0 and this interval that is in this set A, right? So that is a limit point. So 0 is a limit point, and limit point need not belong to the set. Fine. Okay. It's clear. I can go over again if there is any
Yes.
confusion.
Okay, sir. Okay.
Okay. Now, second thing is interior points. Say there is a set A, some set E, like this. Now we say a point P to be interior point if there exists a neighborhood around P that is contained entirely in P. There exists, okay, this is important. There exists a positive R such that this thing should hold. Right, the neighborhood, the way we define neighborhood is set of all the points Q such that distance between P and Q is less than R. And this D is nothing but the metric on the space X, set X. Okay, fine. So here you can see, right, if this, you can draw a ball of some radius which is lying entirely inside this E. So P is an interior point. Let's say if I put P on the boundary, is this an interior point? Can you draw a radius, a ball of some positive radius that is lying entirely within E?
Not possible.
It's not possible, right? It will intersect something outside E. So this is not a interior point. Okay. So now a set is open, a set E is open if every point of E is an interior point. Okay. So that's the definition of open set. We're coming to closed set. This set, any a set E is closed if it contains all its limit points. So in the example that I just gave here, is it a closed set?
No.
Yeah, I'm writing with mouse. Okay, so probably there is some connectivity issue, I guess. Uh, so is my writing faster than speaking, or speaking is ahead of writing?
Okay. It is okay, sir.
Speaking is ahead of writing. Probably, can you join again? Because it's okay for the other. Um, it is okay for Kirti. Can you just try to rejoin once?
Yes, okay, sir.
Oh, it always happens. Hmm. So I am talking from two different places. Last time I was in a different place. So probably you may want to switch your network from if you're on Wi-Fi to phone or phone to Wi-Fi. Okay. So yeah, coming to say this thing, is this set closed? So what I said for closed set, it should contain its limit points. So what is the limit point of this? As I discussed, 0 is a limit point. So does 0 belong to this set?
No, it does not belong to that.
Yeah. So what can we do to make this closed? Just put union 0. Okay. So this is a closed set. Okay. This is clear, right? So a set is closed if it contains its limit points. And what about this set? 1, 2, 3, and 4. Is this set open? So we should always ask in under what space we are doing. Let's say if this set E, if I define like this 1, 2, 3, 4 in R, is set E in R, is this open? Is this open? We can just see the definitions. That's it. I mean, for because it's a one dimension thing, right? You can just have this points, right? 1, 2, 3, 4. What was the definition of this thing? Let's have a problem again. Right. So this is not open set because I mean you just draw any ball, right? Simple ball, right? Around 1.5 to 2.5, around 2. Right. What I told was this ball, this interval should contain entirely inside this set. If you see around say this 2.1, 2.1 doesn't belong to this set, right? So this is not open. So why is this closed set 1, 2, 3, 4 in R?
It is closed.
No,
Why do you think it is closed and why do you think it's not closed?
There is no limit points of E.
Right.
This does
Correct.
not belong. Yes.
Correct. So basically, if you see, right, this set is closed. I mean, it's a tricky reasoning. As pointed out, there are no limit points for this set. Okay. Um, Again, right, you can check the definition of limit point. Uh, if I take if 2 is my limit point, let's say it should intersect for every radius, right? Let's draw some small radius, any radius. Now this ball, sorry, this in one dimensional interval, this ball is intersecting only at 2. But as per the definition, it should require to intersect at any other point other than 2. Okay, so 2 is not limit point, 3 is not limit, 4 is not, 1 is not limit point. So none of them are limit points. So set of limit points are nothing but empty set. But as you know, empty set is a subset of every set, right? right? So that's why you say, I mean, this contains empty set, and set of limit points for this set is nothing but empty set. That's why it's closed. So that's how the argument is. So there's a reason why this is closed. And coming to compact sets, so let's say if a set E is compact in X, a subset of E is compact in X, if let's say you have cover for E, cover means collection of open sets G alpha. This alpha can be finite, no, not finite. In this definition, alpha is infinite, countable or uncountable. Okay. If E is contained in such a collection of G alphas, we call this set of G alphas as cover for E. Okay. Now this set E becomes compact if for every cover that you can write like this, there exists a finite um, subcover G alpha I. Okay. If it's possible to write like this, then the set E is called compact. Okay. Now in R, so this is a very general definition of compact sets. I mean, um, in R, compact sets have a pretty simple this thing. Any set that is closed and bounded is compact. If you are just dealing with R, which is what we are doing now. Okay. The definition is very abstract here, but here this is fine. So for example, what do you think about this set 1, 2? Is it compact?
Yes, sir.
Because it is closed and it is bounded, right? Because all the elements are less than or equal to 2. Now tell me why this set is not compact.
0 is of this set, but 0 does not belong to this set. So
Right.
this is
So you can claim that it is not closed, and 0 is the limit point of this set, and it's not closed. Can you argue on these lines? Is it from this definition? See, so it's little tricky. So let me argue this thing. This can be expressed as a union of these sets.
minus 1 by n 2 1 by n.
1 by n to 1. That's fine. Closed one. Okay. Now, and this is a cover for
That is not
this.
sir.
Okay. Which one?
That is you have taken, sir. Union of
Huh.
one.
Yeah.
So, but G alphas are open sets, na?
G alphas are open sets. Yeah, I mean, okay. Let me do this thing. Okay.
Yes, sir.
Yeah. So now is it possible to take any finite elements of this and cover this? It's impossible, because let's say any, if you take n as some 1 over 100 to 1 and something else, right, and union 1 over 98 to 1, right, I can always find a number that is less than 1 over 100, when which is not lying in this kind of union. Okay, so it's not possible to take any finite subcover and still cover this entire thing. So this is from the original definition, right? And I think, can you come again?
Why there is no such finite subcover
Oh,
of this?
there's no finite. You can give me any finite choice of n. So let's say n naught, n1, and let's say n, what do we pick? np. Let's pick up like this, n1 to np. Okay. Let's say we cover, we think that we are covering this thing, right, with union of 1 over, and we can arrange them in this order. I mean, where n1 is less than np is less than this. Okay, and n I is going from 1 to p. Okay, so now what is the lowest interval? Lowest interval is 1 over np to 1. Okay, and 1 over n1 to 1 lies somewhere here, right? Because n1 is smaller than np. The thing is, if I find any other number greater than np, it will lie somewhere to the left of this, and it is not covered by this set.
Okay, sir.
Okay,
Yes, sir.
so that's the reason. And what else I supposed to discuss today before starting problems? Compact sets, closed, open, and dense sets I think not required. I'll just mention on dense and then start problems. Okay, so dense, say a subset of x, a subset E of x is dense in X if every point of X belongs to E, or it's a limit point of E. Okay. Okay. So I'll make it clear what I meant. Consider two things, two sets, E as rationals Q and X to be a real line R. Now my claim is Q is dense in R because every point of R is Q, or it's a limit point of this Q, right? Any irrational number you can approximate with a sequence of rational numbers. Okay, so that's why we call Q as Q to be dense in R. I think that's what I wanted to tell before we start the problem solving things. Okay, so let's start. Yeah, so I'm having solutions also in the place here. So a subset A of R is open and closed, then A is an interval. Right, so I mean we can call the entire real line and empty set are the only sets that are both open and closed. And you can call, I mean, R you can call as minus infinity to infinity, and phi, I'm not sure how do you express this as interval, but yeah, um, empty set as you can, I'm not sure how do I put it, as an interval. But yeah, so that's the thing. Uh, Again, right, which of the following is true or false? Every subset of R which is countable and compact must be finite.
So can you repeat again, sir?
So every subset of R which is countable and compact must be finite. So this is the first example that we discussed. Set A is 1 over n, right? And what they are saying is any countable and compact set must have to be finite.
Yes, sir.
No, this is not true. What I'm saying is, so if you say this thing, right, a sequence 1 over n that is converging to 0 as n tends to infinity, and we know that is not closed because 0 is a limit point, but you make it closed by appending 0. Now this is closed and this is bounded because all the elements are less than or equal to 1 clearly, and that's why this is compact, and this set is not finite, this is countably infinite. I mean, this is an additional way to verify things, but this is a counter example, that's why this is false. Okay.
Yes, sir. So how do we prove this in general?
I mean, to prove the, I mean, to uh, disprove a fact, it's fine, it's okay to give a counter example. But to prove something, yes, you have to show that for every possible scenario. I got it. To disprove some claim, you just need to give one counter example. That is fine.
How do we, sir, prove this?
Which one? That's what I'm saying, right? So, so this is a claim which is false. To prove some claim to be false, you just need to give one counter example. But if it were to be true, let's say if it were to be true, then it's not sufficient enough to give one counter example. So you need to prove it for every case. So here we just gave one counter example and we call this statement to be false.
Okay.
Okay. Again, right? So uh, is integers, again, they lie inside the reals, one-dimensional reals. Is this closed?
Yes, sir.
Right? Again, right? There are two arguments given here. As I discussed, right? The set, right? The 1, 2, 3, and all in natural numbers, they are kind of closed because they don't contain any limit points. But then I think I forgot to tell a couple of things. So if a set A or E, let's say E, if E is open, E complement is closed. And the other way around. If it is closed, E complement is open. Right? So now what was said is Z as a subset of R. Is this open or closed? The claim is closed, and the way it's been done the other way around is you can call this as a union of n to n plus 1. N belongs to Z. right? So it is leaving out the integers and considering the space between the integers. Fine. And because again, yeah, another important thing I forgot to tell you was arbitrary union of open sets is open. This alpha, this can be countable, uncountable. Again, finite intersection of open sets is open. G alpha I is equal to 1 to n. Okay. So for closed, the other way around, it holds. Okay. This is open, this is open. For closed, this has to be intersection. F are closed. This is union here. F are closed. 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 So arbitrary union of open sets is open. Finite intersection of open sets is open. Arbitrary intersection of closed sets is closed. Finite union of closed sets is closed. Okay. And so these concepts we are using now. Now this is arbitrary union of open sets. And that's why this entire set is open. Now, if we take the complement of this entire set, let's call this as Z. Not Z, say some E, right? And the reason E is open because we are appealing to this result. Each of this is open and the arbitrary union is also open, right? And what is E complement? E complement is nothing but integers here, right? E complement is nothing but Z. And because this is open, E complement is closed, which is another way of concluding that the fact that a set of integers are closed. Fine. Is it clear?
Yes, sir.
And yeah. So this again state whether this is true or false. There are no subsets which are neither bounded below nor bounded above. This is not true. I mean, we can easily cook up a subset like integers, which is a subset of rational numbers. They are not either bounded below or not bounded above, right? They go to minus infinity to plus infinity. So there are subsets. Okay. Again, by the way, you can see my screen, right? The problems I'm flashing. Yes or no?
Yes, sir.
Yeah. So again, right, A is subset of R, B a non-empty. And so this is a non-empty subset. And P belongs to R such that P is the only limit point of A and P doesn't belong to A. Okay. So the best example is what we consider today, like A is 1 over N. The same thing is being presented here. So what is A? Is A open, A closed, or what is it? Definitely A is not closed because it is not containing its limit point.
Sir, it is also not open, sir.
Yeah, right. It's not open. Now, for open thing, it's a completely different story, right? Every point has to be an interior point.
Sir, every open set subset of R must be uncountable.
Every open set of R must be
Non
uncountable.
non-empty, sir.
Non-empty. Yeah, true.
Yes. But this is,
Uh,
sir,
and if to state whether the following is true or false, A subset of R is non-empty and bounded above. That means supremum of A exists. Again, you can define minus A to be just flip the sign of this thing. Then minus A is bounded below. Then is the following true?
sir, your screen is not visible, sir.
It's not visible.
No, sir.
It was visible some time back, is it?
But sir, the questions are not, sir, changing, sir.
How about the other? What's the name? How about Kirti? Can you see the slides changing?
No, sir. No, no, sir. Just questions are not visible. Just whatever you have written with mouse, na sir, that only visible on that part, writing part.
Oh, that's why I asked actually in the beginning. Can you see my slides rolling? Let me.
Sir, why you, sir, do not use some, sir, gadget for writing, sir? It's
Um,
very, sir, mess.
I'll try next time.
Yes, sir, sir, it is not very, sir, appealing, sir.
Yeah. I'll try
Like
next time.
first class student is writing, it seems.
Yeah. That's there. Um, but I hope content is appealing.
Yes, sir, yes, sir.
Yeah. So can
Yes,
you
sir.
see
Yes.
this? Can you see the slides now?
Yes, sir. Right now it is.
Right. So yeah, I'll see if I have gadgets. So last year I was taking some other course. I had some problems with using gadget. Let me experiment in the upcoming week, and let's try to pair this time. Okay. Um,
Yes, sir.
so here's a question. This is a question, right? So a subset R, which is non-empty and it is bounded above, right? Again, you define minus a as flipping of every element of A. The question is again, minus A is bounded below. Is this true? Infimum of minus A is minus supremum of A. This is true. I mean, I'm flashing the answer as well. Do you want me to prove this? I mean, solution is all written, but do you want me to prove this? I mean, this is very simple. You just need to use the definition of a supremum and just flip the signs. Your inequalities will be just flipped accordingly, and you will get this result. Okay. So I'm not spending time on this. Or if time permits, we'll come back to it. We can see the other interesting things. Yeah. So this is a difficult one. And now we have INs like this: AN, BN, closed A and BN, and N belongs to positive integers. Now these are closed and bounded, as you can see, right? The closed sets and bounded. But then IN intersection IM is not equal to empty. So that means you take any finite subset of these intervals, their intersection is non-empty. Okay. The question here is, if we take intersection of infinite such intervals, which of the following is true? So the answer, the true answer is it is non-empty closed interval. Now the conclusion that it is closed interval is simple because of our earlier thing, right? Arbitrary intersection of closed sets is closed. Okay.
Yes, sir.
Now, how do we conclude that it is non-empty? That is the difficult part. Okay, so let me attempt this thing. Proof is little involved, so let me know wherever you are missing anything. So I'll just prove this for general case. Now the closed and bounded reals are nothing but compact, right? Compact this thing. It's compact sets basically. So this thing, these are sequence of compact sets K such that you take any finite number of K alphas from this set and do intersection of K alpha I goes from say 1 to n is non-empty. Okay. Now in this case, the overall this thing intersection K alpha is non-empty. Right. So this is a statement. So the thing is, let's enumerate this. And I call K1 to be one of the elements of this set, and remaining are let's say the other elements. Now assume that this is empty. On contradiction, you can assume this is empty. So when do we get this as an empty set? Let's say one of the element is K1, right? So notice that this will be empty if any element of K1 cannot present in all of K alpha. Right?
Yes, sir.
But right, if any element of K1 is present in all of K alpha, then it is non-empty. That element itself is present in the intersection. Right? So then what we can conclude is this K1 belongs to complement of this set. Because we said K1, any element of K1 cannot belong to this set, right? In this K alpha, we removed alpha minus 1, okay? We removed this one element of this one. That's why I'm denoting this by alpha minus 1.
Yes, sir.
Okay. And now if you see this, whatever the alpha minus 1 intersection we are taking, if you expand this thing, what it will become? Union of alpha minus 1 times K complement of alpha minus 1. Why is this true? What is this law called? This to this.
De Morgan's law.
De Morgan's law, right? De Morgan's law. Fine. Now, K is compact means in our case it is closed and bounded. Okay. Now, what is K complement? So K is closed. K is closed. Okay, so K complement is open. I'm using the property that complement of closed set is open. Okay, so each of these elements are open set, and each of these Ks are compact, right? You know, by the definition of what we have from compact sets, now you can find a finite subcover within these alpha minus ones, right? You can find some n is equal to, so sorry, ni, some ni's, such that this K is contained in K complement ni. I is going from say 1 to L. Okay. This is happening because we assume K1 is compact, right? From this infinite thing, you got to finite thing because of the definition of compactness. Every infinite cover has a finite subcover. Okay.
Yes, sir.
So what does this mean? Now K1 intersection of these things, right? Union of what should I put it? Union of, say, let's try to write, this is intersection K N I whole complement, right? So this K1 is contained in this intersections complement. Okay, this is again I use De Morgan's law. Clear? How from this to this, it should be clear. I goes from 1 to L. So that means what is happening is, if I intersect K1 with this internal thing, right, it should be empty. I is equal to 1 to L K and I. This should be empty. Yes, because K1 is lying in the complement of this set. But if I intersect this, so basically it is this, okay? Say this ball is E and this is E complement. The rest of my white space is E complement. Okay, and this ball is E. And what I'm saying is K1 belongs to E complement. K1 is here, is this here. What happens if I intersect K1 with E? It's empty. There's no intersection, right? Is it clear? And where it's not clear, you can let me know. I'll go over again.
Sir, please explain again, sir.
From which point?
From where you have written, sir, K1 is subset of finite, sir, subcover.
Oh, cool. So this is clear, right? Up to this point.
Yes, sir. This is by
This is
definition.
clear. Now K1, because K1 is compact, what I earlier told is every infinite cover, countably or uncountably, will should have
But
a
this is,
finite subcover,
yes, sir.
right? So that's that property I'm exploiting. So I can find some subsets K alpha that can still cover my K1.
Yes, sir.
So that is possible because we are assuming K1 is compact.
Yes, sir. Yes, sir.
So now from this, so I'm assuming N1 to NL are some indices of K1, this K complements that can still cover my K1. This is nothing but again use my De Morgan's law. Again, this will become intersection of K and I complement, right? So
Yes.
what all I'm using is if A is a subset of B complement, A intersection B is empty.
Sir, okay, sir.
This is a property I'm using.
Yes, sir.
This is true, right? So that is what I've written here.
Yes, sir.
But then what we have assumed is any finite number of K alpha should have non-empty intersection. That's what we have assumed to start with,
Yes, sir.
which is a contradiction. I have produced a finite intersection of K alphas, which is empty. Hence,
Yes,
our initial assumption must be wrong. So intersection of K alpha is non-empty. If it is empty, you lead to contradiction.
yes, sir.
Okay, this is little involved. So, but then I think it's fine. Okay, so that's why it's non-empty, and why it is closed. It's fine. I mean that because infinite intersection of closed sets is closed. Okay, so you can see the question 8, right?
Yes, sir.
Yeah. Again, right? This is a big long solution. I'll argue in a very in an alternate manner. So R minus Q is neither open nor closed. The reason is Q is also neither open nor closed because the limit points of Q are all the irrational numbers, right? That's why Q again, right? The set Q by itself, it doesn't contain irrational numbers. So Q doesn't contain its limit points. That's why Q is not closed. And because of density of this thing, the Qs, right? You take any open set around Q, any element of Q, it contains irrational number. Again, it will not, that irrational number is not in the set Q. That's why it is not open. So Q is neither open nor closed. Its complement, it follows that its complement will also be neither open nor closed. Okay.
Yes,
Yes.
sir.
Yeah. You can go, I'll upload this sheet. You can go this form, this alternate solution. Okay.
Okay,
But,
sir.
but I feel that that's the elegant way of arguing things. Does anybody wants to join? Okay. Again, this is very simple. You should be able to answer this. A is open, B is closed. Which of the following is true? Let's directly go to solution and justify why it is true. A minus B is open, B minus A is closed. So what is A minus B? How do we write in unions and intersections? Any idea?
Sir, A minus B is A intersection B complement.
Right. A intersection B complement. Now, what is B? B is closed. So B complement is open. And you know, finite intersection of open sets is open. That's why A minus B is open.
Hmm.
Okay. Again, the same thing goes here. B is closed, A is open, A complement is closed. You know that any intersection, any number of intersections of closed sets is closed. So here you are intersecting two elements only. So it is closed. Okay.
Yes, sir.
Yeah. Is there anyone wants to join? You can allow. Okay. Think we're almost done. Yeah, I mean, this is the last question. Uh, which of the subsets are, I mean, which of the following are true? Basically, it's on the compactness. Um, because we are dealing with R, compactness is equivalent to saying closed and bounded. So first is closed because union of two finite union of closed sets is closed, and bounded. So A is compact, and B, it's not compact because it is unbounded, right? So positive infinity. Finally, C again, this R minus Q, we just saw this is neither open nor closed, right? When you intersect such a set with 0 to 1, it still will not be closed, and hence it's not compact. Okay, so A is compact and B and C are not compact. Any questions? So as you have suggested, I'll start using this thing, uh, tablet from next session. And yeah, any questions? I'll try to answer. Otherwise, this is what we have for today. So these are useful, right? These problems or these sessions. And
Can you include some good questions like from some CSI or net exams? Question from
I can do that. If you want, I can pick up some difficult questions. I mean, you want something on these lines, right? Is it?
yes, sir. From compactness and like
Yeah, yeah, yeah. So next week, then in next week sessions, we'll solve certain problems on compactness.
yes, sir.
You know what is Heine-Borel theorem?
No, sir.
Oh, shall we do that next week then?
Yes, sir. The problem
Okay.
I want, sir, some problems on that theorem, sir.
Yeah, I will prove the theorem and maybe 2-3 problems. Maybe not 2-3, maybe too much, but definitely one problem around that.
Yes, sir. Sir, is the theorem is that every compact set in R is closed and bounded.
Right, right, right. So that's what the fact we were using left and right?
Okay, sir.
It comes from that.
Okay, sir. Sir, please include, sir, some problems from that theorem, sir.
Yeah, yeah, sure, sure,
Okay,
sure, sure. I'll do it. Okay then. Yeah,
thank you, sir.
yeah. Thanks. Bye. Let's
Yes,
meet
sir.
next week.